Hi, and welcome to our next video here in our chapter on information theory. Today I will simply continue our discussion on the basic properties of entropy. I will also introduce the concept of joint entropy, which is a straightforward generalization of what we did before. We'll talk about the uniqueness theorem by Khinchin and figure out that there's basically just one choice to define entropy if we are accepting a very small set of basic properties of entropy, exactly the ones that we already discussed. And I'll also introduce the principle of maximum entropy. So let's dive right in. So here we'll begin with a further example, the simple calculation of entropy for a Bernoulli random variable. So random variable with just two outcomes. So we have one outcome which is called success. We usually encode this with a 1, and a failure which we encode with a 0. So of course this is basically a coin toss, heads or tails, but not necessarily a fair coin toss with a 50-50 probability. So we now have a success probability of S. So that's just our symbol here for P of x equals 1. And we have the counter probability 1 minus S, which is simply the probability of observing a failure, of observing a 0. And the only thing I now want to do here is I want to plot entropy of this Bernoulli random variable as a function of the success probability S. So as you can see, I've marked one point here. So where the success probability is 30%, can see the distribution here on the right hand side. So apparently it's 30% for x equals 1 and 70% for x equals 0. We can now calculate the entropy by applying exactly the formula as we have introduced it before. And here in this graph here, you can now see the entropy for each and every success probability S. Note that as we have discussed before, if we have a deterministic coin, so that would imply S equals 0 or S equals 1, then our entropy is of course 0. And also note that entropy is maximal for a fair coin, because a fair coin has a uniform distribution, so a distribution with 50% for 1 and 50% for 0. Now for all other success rates, the further they are away from this point of maximal uncertainty, from this uniform distribution, the lower the entropy. So you can see how entropy goes down if we go left or right, and approaching either S equals 0 or S equals 1. Okay, so as promised, we can now also introduce the concept of joint entropy for a bunch of random variables. So let's start with two. Let's start with two random variables x and y. And we can now write the joint entropy here, either as a function of x and y or as a function on their joint probability mass function via this double sum here, where we go over minus probability times log of the probability of this joint probability mass function. So I won't read out the formula. It's a straightforward extension of what we've seen before. This should be immediately plausible to you. This is also very consistent with what we did before. We could even see this as the entropy of a single vector-valued random variable, where we sum over all of the combinations of events from x and y. So of course, we can also do this for more than two random variables, and this just simply results in higher dimensional sums, so to speak, over the probability mass function. So nothing too surprising going on here. Now, but what we can now do with this very basic definition is we can prove an extremely important property of entropy, and this is that entropy is additive for independent random variables. So let's assume we have two random variables x and y, and they are actually independent. What we now want to show is that the joint entropy eta of x comma y is actually eta of x plus eta of y. So is this very hard to show? No, it's, I don't know. There's some lengthy formulas going on this slide, but the proof is very trivial. So we start by plugging in. I won't read out the formulas. It's actually quite boring. So we start by plugging in the basic definition of the joint entropy. Then we note that if our random variables are actually independent, well, what happens with the probability mass function? It factorizes. So we do exactly that here. Oh, probably we also do it here. That's very nice. And now the next thing we can do is, well, we see that our log function here nicely transforms this product of px and py into a sum. Okay. And then we, rearrange terms a little bit, and we see that we end up here with our, with two terms which are exactly the entropy formulas for x and y. So we basically just use two things. So we use the fact that for independent random variables, the probability mass function factorizes into a product over the marginals, and we use the fact that the log function turns a product into a sum of the logs, and that's just it. So very simple proof. I guess you could have done this here even without me putting it on the slide. Okay, as I said before, there's now also a very nice uniqueness theorem, which tells us that everything that we have defined up to here, which was mainly our basic definition of the entropy formula, is very reasonable, and we don't really have a lot of different choices. So Kinshin showed in 1957 that there's basically only one family of functions which satisfies the following the following axioms. So if we assume that, let's assume we want to introduce some measure of uncertainty which acts on a probability mass function. Let's require the following properties of that measure of uncertainty. So first of all, it should be continuous in the probabilities, p of x of the probability mass function. Second, adding or removing an event with probability 0 does not change it. It is additive for independent random variables, and it is maximal for a uniform distributions, for uniform distribution. And all of these properties we also discussed here. Then this measure must be of this form here. So this is basically our entropy formula up to one multiplicative constant, which I call lambda here. And this positive constant is basically fixed by fixing the base of the logarithm. So there's basically only one choice, and this is to accept that all of these things here make sense, and I guess we should probably accept these things. Then there is basically only Shannon entropy up to the base of the logarithm. That's pretty nice. So I want to wrap up now, or well, not wrap up, or let's say finish with the also quite important principle of maximum entropy. So let's assume now that we are, so this is a principle of deriving a distribution under certain assumptions of the distribution. So let's assume that we know m properties of a discrete distribution p of x, and these are stated as so-called moment conditions. So we are being given some functions gm and some scalars alpha m, so that the expectation of this function gm of x equals alpha m. So we have a finite bunch of them, so g1 and alpha 1, so then the expectation of g1 applied to x equals alpha 1. Maybe there's a second condition g2, so there's a function g2 on x going on. If we take the expectation, then this also equals alpha 2. So then we might have a bunch of these moment conditions, and the question now is, how do we figure out what our distribution p of x now is? And this is exactly the maximum entropy principle. So the idea is here to, well, of course, adhere to these constraints. And then among all feasible distributions that satisfy these constraints, we'll simply pick the one with maximum entropy. So the one with maximum uncertainty. So yeah, of course, the idea is to assume nothing else except for the given constraints. And then this maximum entropy principle basically follows a certain similar logic to Occam's razor, or this principle of insufficient reasons. So I'll just pick the one thing that is most uncertain, but adheres to these given constraints. Now it turns out that there's actually a nice way of solving this. So we can solve this via Lagrangian multipliers, which shouldn't be super surprising because we are giving these bunch of constraints and this objective function to maximize the entropy. And here I will do this with, I don't know, for some arbitrary reason, with respect to base e in the logarithm and not log 2. So yeah, I can use the natural logarithm and the exponential function. So I can now write down the Lagrangian to solve my optimization problem and then see where that brings me. So I will write down my objective function, which is simply our entropy formula. And this now works in a very similar way to what we did in the unit before with respect to showing that the uniform distribution actually has maximum entropy. So we write down our entropy formula here, want to maximize that. And now we write down all of the constraints that we're being given. So the first constraint that we always have to adhere to is that our probability mass function sums to 1. And then here we have all of these constraints from the moment condition. Okay, so we just, as for this guy, we rearrange everything. So we have a 0 on the right-hand side. We put a Lagrange multiplier in front of things, and then we put everything together in our Lagrangian. Well, and now we look at that. So, well, we look at it, and we already know what kind of the next step is. We now need to find critical points of this Lagrangian. So we want to find points where the gradient is 0. So let's take a look at all of the partial derivatives. So I'm not sure how much I'm going to read it out, maybe a little bit. So it's in a certain sense, okay, let's take a look at it together. So first of all, we now take a look at, actually, let me remove some of my scribbling so it becomes a little bit cleaner. So first of all, we take the derivative of this guy here. So yeah, we did that before. This is simply minus log pi of x, because if we take the derivative of this first guy, this becomes 1. Of this guy here, it becomes 1. So we are left with log p of x. And then we take the derivative of this guy, and this is going to be p of x times 1 divided by p of x, which is simply 1. So we now have found this term here as well. Now let's take a look at this here. So we have a sum over multiple p of x's. Take the partial derivative with respect to p of x. So there's only the one guy with respect to x left. This becomes a 1. We multiply it with lambda 0. So we have now found this thing here. So now there's only this sum left. So what happens now is that the outer sum, this here, stays. But for this inner sum, again, everything vanishes except the term with respect to the x that we're taking the partial derivative with respect to. And then we have simply here lambda m times gm of x with the x that we are differentiating with respect to, and then the p of x becomes a 1, and this alpha here vanishes because it doesn't have a p of x in there. So that's fine. We have now found the formula here for our partial derivative. We set this to 0, and we now simply solve for p of x. So how do we do that? Well, fortunately, there's only one term with p of x in there. We bring that to the left-hand side. There's a minus log, so we bring the minus to the right-hand side, and then we take exp of everything on both sides. The exp turns all of these sums into products. Well, or at least it turns this thing here into a product. Okay, And now if we want to, well, I guess we better check that we are actually at a maximum. So we can also take the second derivative. So let's do that very quickly. So for the second derivative, we look at the first one, we take another, differentiate again with respect to p of x. So everything here vanishes, and log of p of x becomes, or minus log of p of x becomes minus 1 divided by p of x. Very obviously, this is negative. So if we have a negative second derivative, I guess our function is convex at that point. So we are actually at a maximum. The next thing we can do is we know that probabilities, all of the probabilities of our probability mass function, p of x, they need to sum to 1. So we can write that down, can insert this formula that we are given here, and because we now have one equation, there are a bunch of unknowns in there, we can actually eliminate one unknown. The one unknown we want to eliminate is this lambda 0 thing here. So let's simply insert this formula here. So the only thing I now did is that instead of multiplying with x of lambda 0 minus 1, I divide by x of 1 minus lambda 0. Yeah, so yeah, kind of just do a minus here inside of the x function. That allows me to bring this, sorry, pen tools again are not working. I bring this here to the left-hand side. I have it now here. And now I have a nice expression for x of 1 minus lambda 0, which is this here on the right-hand side. And I can now plug this in here, which allowed me to eliminate the term with the lambda 0. And I have now this formula for p of x. So that gives me a kind of a solution for my probability mass function based on the maximum entropy principle. Now, of course, well, we have now a functional form for our distribution. Maybe let's stay here a little bit. So this thing is already pretty nice. So now we have a certain functional form for p of x. It's not completely solved. And there's also a bunch of unknowns in there. So we've solved it partially, but we have all of these m unknowns here, these lambda m's, these Lagrangian multipliers. So we know the form, but there are m unknowns in there which we don't know. Can we solve that? Yeah, we can, because we're also being given m equations, because we're being given m moment conditions. So we have now m equations in m unknowns. And these equations are not necessarily linear. They might be nonlinear, but in any way we now have m equations in m unknowns, and that means we can at least usually numerically solve that. Yeah? So you can use something like the Newton algorithm to numerically solve that. So you get all of these, you get all of these variables, these lambda m's. Then you can insert them into this functional form, and then you really have the exact specification of your probability mass function. And here's a very simple example with just one moment condition. So let's consider a discrete random variable which represents a 6-sided die. And we have a moment condition, so it's not necessarily a fair die. And we have a moment condition that the expectation of that x, of that random variable, so the expected number of points we get when we roll that die, is 4.8. So what is now the maximum entropy distribution under this moment condition? So let's write down our moment condition. So we have one function g of x, and that function is the identity, because we have the expectation of x with no function acting on x on the inside, so or the identity function acting on x, and on the right hand side our scalar value is 4.8. So now we already know how the functional form of our probability mass function is. It's x of lambda times g of x. G was the identity, so it's just simply x of lambda times x, and there's just one lambda because there's just one moment condition. In here we sum over all of the events of the probability mass function over x of lambda times xj. So that's our functional form. Just this thing here. I'm not sure how many arrows I'm going to draw here. It's just exactly this thing copied over with 1 lambda m. So we know this thing now, or we know that our probability mass function has this form. Yeah, so it has 6 of these terms. And what we now have to do is we have to find the lambda in these terms. And exactly, we now do exactly what I said before. We use our moment condition. So we have one equation and we write down our moment condition. So the expected value of this thing here is 4.8. Yeah? We plug in the functional form we are given of our probability mass function. This has one unknown, the lambda, and now we have this nonlinear equation going on here. So we have one nonlinear equation with one unknown, the lambda, and we simply now numerically solve for that, which gives us a lambda of approximately 0.5141. We plug that into this functional form, and we can now write down the probability mass function exactly like this here. Now, that's it. Could have also done this for a fair die. So then we would have assumed that E of x is 3.5. That would be the expectation of a fair die. And then you can very easily, without resorting to numerical optimization, see that this is solved with lambda equals 0, which gives you the uniform distribution with 1 divided by 6 as a probability for each event.